All right, hello everyone, and I am going to explain problem 6 of tutorial 4 because there was a request to do it. All right, here is the problem. So here we have a cardboard box without a lid, and it has a certain volume, and we need to find the dimensions of the box, um, which minimize, I think that there is a grammar error here, which minimize the amount um, of cardboard used, right? So what is this about? It is about a cardboard box, so it is something like this, um, right? So here is a cardboard box without a lid, right? So there is no, so it is not covered from above, so it's probably, I don't know, something like this. And we need to minimize the amount of, so the volume is fixed, and we need to minimize the amount of cardboard. So in other words, we need to minimize the, essentially the surface area, right? So the cardboard consists of the bottom and the four sides. So let me draw an illustration here. So it looks like this. So this is something like, well, I guess, yeah. This is our cardboard. Well, I hope it makes sense. All right. Now, its dimensions are going to be, let's say, x, y, and z. So we need to find x, y, and z to minimize the amount of cardboard used. So this is a method of Lagrange multipliers. So we have a constraint. So the constraint is clear, right? So our constraint um, says that the volume, which is x times y times z, is 32,000 cubic centimeters. Well, let me write it as minus 32,000 is 0, right? So um, I'm going to denote this as g of x, y, z. Now, what is the objective function that we need to find the minimum of? The objective function is the amount of cardboard used, right? So, but the amount of cardboard used is essentially just the surface area um, of our cardboard box, right? So the surface area is what I mean. So if x and y, if the let me highlight the bottom here. Let's say that the bottom of our cardboard is going to be, well, this is the bottom of our cardboard. Okay. So the bottom is x by y. So which means that the objective function f of x, y, z is going to be x, y. This is the area of the bottom plus the area of the four sides. So, and the four sides are x, z, y, z, and another copy of x, z, and another copy of y, z. So this is going to be x, y plus 2x, z plus 2y, z. So this is the objective function. All right, so now notice that we assume that the global minimum exists. Okay, so we do not have to prove it. And believe me, it is kind of tricky here. So we just take it as granted. So another thing that probably should worth mentioning is that we are working with a real physical box. So which means that x should be positive, y should be positive, and z should be positive. They are dimensions of the cardboard. Okay, so when we solve the system of equations, we can just apply these inequalities. Okay. All right. I hope it makes sense. Then the next stage is to write the Lagrange function. The Lagrange function is f minus lambda g. All right, so let me rewrite again. So f of xyz is xy plus 2xz plus 2yz, and g of xyz is xyz minus 32,000. Okay, so now we need to set up the system of equations that comes from the method of Lagrange multipliers, right? So the first equation is the partial derivative of L with respect to x. It is going to be y plus 2z minus, well, basically this term is lambda times whatever, whatever this. So it is going to be lambda yz, and this should be equal to 0. Partial derivative of the Lagrange function with respect to y is x plus 2z minus lambda xz should also be 0. Then partial derivative of L with respect to z is 2x plus 2y minus lambda yz, right? Here should be 0. And partial derivative of the Lagrange function with respect to lambda is just minus x, y, z minus 32,000 should also be equal to 0. And the last equation is nothing else but our constraint, essentially, right? So let me, just change it a little bit back to our constraint. Because essentially, the last equation just tells us that x, y, z, that the volume is 32,000 cubic centimeters, right? So besides, let me again write the fact that write the inequality x, y, and z are all positive, strictly positive. All right, so how do we solve this system of equations? Now, if you look at it, there is no clear method. It is a nonlinear system, so there are terms of degree 3, products of 3 variables, and it's not really clear how to do it. And usually, when it is not really clear how to do how to solve such a system of equations, then sometimes there is a neat trick, and I believe that the official model answer contains some trick to do it. But if I were you, I probably wouldn't really pay too much attention to that trick. I think what really works and what is kind of a foolproof method is if you just try to exclude all the variables from the first equations and substitute to the next equation, right? So, and usually I think what works is, what if we try to, I don't know, exclude lambda, because lambda is our Lagrange multiplier and we don't really need it. I mean, in the end of the day, we are interested in x, y, and z. We're not interested in lambda. So lambda is kind of the auxiliary variable that just helps us to set up the system of equations, right? So let us try to exclude lambda. So from the first equation, lambda is, we can move this to the right-hand side and divide by yz, right? So from the first equation, lambda is y plus 2z divided by yz. So notice that I divided by yz without caring that y or z can be 0, because I already know that y and z are strictly positive. So from the second equation, because of the same logic, lambda should be x plus 2z divided by xz. And from the third equation, lambda is 2x plus 2y divided by yz, right? Sorry, yx, of course, yx, xy. This should be xy. xy yeah. Okay, Now, so what do we do then? So notice that these are all equations for lambda, right? So basically, it means that, but lambda is the same, right? So it means that, you know, this equals this and this equals this. So we can just um, use it as two new equations. I mean, we can exclude lambda by just equating, you know, this to this and probably this to this. All right, I hope it makes sense. Or maybe like, um, maybe just because of some symmetry here. So let me do the following thing. So let me do this. And I'm just trying to, you know, to reason, to reason out loud. So I guess what makes sense is because of the symmetry. So we can equate this, the third equation and the second equation, and the third equation and the first equation, right? So I know that y plus 2z divided by yz equals 2x plus 2y over xy. So because both of them are equal to lambda, right? So both of them are equal to lambda, but you know, the whole point of this is to exclude lambda, so I don't really care about lambda anymore. All right, so let me try to simplify this. So both equations have y, so I can cancel by y. Now I can multiply by xy. So multiplying by xy, I will get xy on the left plus 2xz equals, on the right I will have 2xz plus 2yz. Cool. So now I have 2xz on both the left hand side and the right hand side. And once I deleted this term, I also have y on the left hand side and on the right hand side. And finally, this simplified to just x equals 2z. Right? So which means that I expressed x in terms of z. And then I can replace x with 2z in the last equation. And probably because of symmetry in x and y, so you know x and y they play the same role, I will be able to do the same thing for y. So let me try. So now um, this equation was if this is 1, this is 2, this is 3, right? So this equation came from equating 1 to 3. So now let me equate 2 to 3. So x plus 2z divided by xz equals 2x plus 2y divided by xy. All right, so now x is on the left hand side and on the right hand side, so I can cancel it out. So now I can multiply by z and y, so then the left hand side becomes yx plus 2yz equals 2xz plus 2yz. Now, okay, there is 2yz on the left and on the right. And now there is x on the left and on the right. So the remaining part is just y equals 2z. Cool. So now we are almost done, actually. So all this stuff is probably not needed anymore. So now the first three equations that looked incredibly complicated at first, they actually boiled down to some very simple relations. So, and these simple relations are just x equals 2z and y equals 2z. So now we can plug it in the third equation. So x is 2z times y is also 2z times z equals 32,000, right? So z cubed equals 32,000 divided by 4 is 8,000. So I guess z itself is going to be cube root of 8 is 2, 20. Okay. and x is 2z. X is 2 times 20, which is 40, and y is also 2z, which is also 40. So that's the answer. So the answer is 40, 40, 20. So notice that we were guaranteed that the minimum exists by the question itself. And since we only found one candidate point here, it must be that minimum. So that's basically all. And there is an official model answer here. Well, I guess the constraint here that there is a typo error, so it should be 32,000. So let me just scroll forward to see if I got the answer correct. Yeah, so x equals y equals 40, and that is 20. So I got it right. So that's all I wanted to show to you.